Hello there. Today, I'm going to be going over the absolute basics to get a screen on the Game Boy Advance that does anything at all. So if we run basically an empty program, the main program, it's just a loop, we get a white screen. And if we do this strange action here, we can rebuild the program, and now it's a black screen. So that's just exactly what this is doing is unimportant at the moment. It's just sort of a proof to ourselves that we can change the program and change what is happening in the emulator. However, there's quite a number of files that we have to set up before this can happen. I'm going to be putting these in. I've got a GitHub repository called GBA dev streams, and I'm going to push this up there in a moment. First, we're going to have a .cargo config.toml file. This will apply additional automatic configurations to cargo every time that we use cargo, because we'll be programming this in Rust. I hope that you like programming in Rust. If you don't like programming in Rust, these explanations will probably be understandable to people that use other programming languages. But maybe learn how this works and then make your own YouTube series for Nim or Zig or whatever cool language you want to use. So our build, we're going to be using the Thumb V4T None EABI target. We need to use the build standard and have it build the core crate because that target is tier 3, so RustUp doesn't ship any pre-provided binaries for it. So we'll have to build them ourselves using this unstable feature. And when we're working on that target right here, we're going to apply some additional Rust flags. Specifically, we're going to pass a compiler flag linkarg equals, and then this thing here, this -t GBA link script.ld. So what does that do? That provides an argument to the linker. Which linker are we going to be using? We're going to be using the ARM none EABI LD linker. And then we can ask it for its help file. We can put it into target help.txt, for example. So we can see all these different arguments here. So many of them. But if we see capital T file name is read a linker script. So this provides the linker with the script. First, the compiler creates object files. The object files get passed to the linker so that it can create a single executable out of all the object files it's given. In this case, it's going to create an ELF file, which is it's a file format used on Linux for executables, and also the linker that we're going to use, we'll talk about MGBA, is going to be our runner. So when we do cargo run and then a binary name or an example name, instead of trying to run the executable directly, this target thingy, this thing here, instead of trying to run this directly on the host machine, it will pass this as an argument to the runner. In this case, MGBA will see the file name, open up the file as a ROM file. It knows how to interpret the ELF format, and then it will play our game. To turn an ELF file into a ROM file that we could flash onto real hardware, there are some additional steps, but for basic programming like debugging and while we're working, this is sufficient. We'll cover those additional steps in a future video. However, we do need to have, you're going to want the GNU ARM embedded toolchain, which provides the linker that we are using. You can get this from, if you go to, no surveys, please. If you just type in ARM bin utils, then you can either get the GNU ARM embedded toolchain and then go to downloads. and then they will have downloads for Windows, for Linux, for Mac. If you've got a package manager, which most Linux and Mac people tend to do, you can often get the ARM bin utils through your package manager. The exact package name varies from distro to distro, so like look around in whatever distro. When it's working, it should install to your path. You may have to refresh your command console. If you've got a terminal open, you may have to close it and open a new one so that it can see the changes to your path. And this funny looking thing, ARM none EABI, all of the tools that we'll be using for the Game Boy Advance in the ARM bin utils are ARM none EABI. In this case, LD is the linker, so we can say check our version. We also have AS, which is the assembler. The linker and the assembler will be automatically called by Cargo and Rust when they need to. However, we also might, for example, use the objdump program, which lets us inspect the ELF files that we're getting to see if everything is turning out right. We would also use objcopy. That's one of the steps in like creating a ROM file. So we need to be sure that we have the bin utils, and we need to be sure that they're in our path so that the Rust compiler can find them when it's time to do it, such as during linking. That's it for config.toml. Let's see. In my settings.json, I just have it so that Rust Analyzer will not check all targets. This is important because when we're building, the test crate will not be built for the GBA target, so it'll constantly think that there's build errors if you have it set to do all targets. I think this may be off by default, and then I turned it on, and I just need to have it off for this one project. But if Rust Analyzer says that it can't build the test crate, that's what's going on. It's just a thing that happens. When I was setting up this project in the past hour, this thing hit me again. It's easy to forget because you set it once and then you never think about it again. Here's that's our example. We'll talk about this last. Next, let's talk about lib.rs. So this is a no standard library, and that means that we will still be able to use the core crate. We will not be able to use the alloc crate. We could if we set up a global allocator, but right now we don't have that set up, so we can't use alloc. And we won't have access to the standard crate. But most of what specifically the standard crate provides is like networking and files and stuff, which doesn't really make sense in the Game Boy Advance in the first place. Things that we would be using in the Game Boy Advance, like integer functions or like string handling, like string slice, maybe, that would be all done by the core. Like slices, options, result, that's all in the core crate. So most of our Rust niceties will still be available. Next, we're going to need a panic handler function, because this is something that needs to exist once in the entire executable. It could be in the example, it could be in this example file, or it could be in our library file. However, as we go along, we're going to want we're probably not going to want separate panic handlers per program. We're just going to want to upgrade our panic handler once, and then every single program would get our panic handler upgrades. So we're going to set it, we're going to write it for the library for our use case. Depending on how you do things, maybe you want to have it on a per executable basis, that's fine. But this panic handler attribute is what defines what the panic handler is. The name, it could be like foo, and like that wouldn't affect it. The fact that it's called panic handler, it's the attribute that sets it. And then if you try to set this more than once, Cargo will say, hey, you can't do that. It accepts a panic info and then returns nothing. So as soon as a panic happens, the panic handler gets called, and then the panic handler is never allowed to return. So later we might want it to print debug output to the MGBA, like it has like a debug out thing. We might want to do that. We might want to have it reset the Game Boy Advance, or we might want to have it like power down the Game Boy Advance, like turn off all the video and then, and then the user would like flip the switch and reset it or something. We'll think about that later. For now, it just does a loop, which is, the program gets stuck. In addition to the panic handler, when the device first turns on, it runs some BIOS startup code. This is like in a little tiny chip built into the Game Boy Advance. And after the BIOS has completed what it's doing, it will jump to the start of the ROM. What's at the start of the ROM is set by the linker script here, so in the config, when we set use GBA link script.ld, this file here is that file. It sets an entry, it describes some memory, and then it describes some output sections of the ELF executable. Text is like program code. RO data is read-only data. Data without the RO prefix is mutable data that is assigned a non-zero initial value. So if we had a global and the global started at a value of 2, for example, then the symbol for that global and the space for it and stuff would go in the data section. And we actually are supposed to initialize that before Rust starts using the assembly runtime we're about to look at. And then there's also this thing called BSS, which is also for global variables, but the BSS is blank static storage or blank storage space or something. Anyway, it starts 0 initialized. So there'll be like 2 different types of sort of pre-Rust initialization that we will eventually write. One is where we have to copy some values from the ROM into the RAM. And then the other one where we just leave it alone because it will have been zeroed out by the BIOS's reboot. Or we could zero it out ourselves, whatever. But when it goes to this text section, the text is the first thing in the ROM. We also have 2 other places where memory exists in the Game Boy Advance that the linker might need to know about. There are more than just these, but these are the 3 that the linker might need to know about because these are the 3 places that code might go. We have ROM, internal work RAM, which is a small amount of RAM where some BIOS stuff goes and our program stack goes, and a small amount of it's only got 32K, but we can also put some global variables there. There's also EWRAM, which is slower to access, but it has 256K instead of just 32K. So if we have some bigger globals, we might put them in EWRAM. The ROM is 32 megabytes. So on a newer embedded device, you might have like a fast CPU and like a lot of RAM, but a really small amount of ROM. That's how some people have described some of the embedded devices I've heard people talk about. The GBA is the opposite. We have huge amounts of ROM, but not much RAM to work with. So we can put a lot of images and sound, relatively speaking, into our game. But while the program is active, we're a little constrained in how much space we have to work with at any given moment. And so you don't need to, if you want to, you can just type in GNU linker manual, and you can get this and learn how linker scripts work. But the details are not important to what we're doing. The basics are that this names an output section, and then these list things that go into so the mapping is like source files to output file. So first, the .text.gba ROM header from any source file will go into the text section, and then these other types of text from any source file will go into the text section next, and then all that goes into the ROM, and so forth. And it's describing these different sections from all the different source files going into the final output executable. And this means that we need to provide if we provide the ROM header, it will go first. If we don't provide this, the linker actually won't care. And so when it all goes at the start of the ROM, that's where our program is going to start. What the actual format looks like is that we're going to use this thing called GBA Tech, and we're going to use it quite often. It provides references for the Game Boy Advance, Nintendo DS, and DSi, as well as general ARM CPU stuff, because that's the chip that these use. And it's incredibly long because this version is all in one single page. If we check the GBA cartridges section, and then we go to the GBA cartridge header section, the header has a 4-byte ROM entry point, which means a particular instruction, branch to, and then some label. And then depending on the address, the actual branch instruction will be like branch plus 16, branch plus 32, whatever. And then after that, it follows this format of like, this is not code. Like, this is a Nintendo logo. That's just a bunch of bytes. There's this game title that's like an ASCII string where we can like put a 12-character ASCII string. The game code, which is like always 2-character, and all that stuff. We don't care about that stuff. But for our program to be usable on real hardware, or even for it to be usable in an emulator, we have to match this format. This isn't really related to Rust programming. This is just related to how the Game Boy Advance works. Any programming language will have to match this format. So we're going to have some special header, which we are providing in this special section. And the way we get that into our Rust code is that we have to use a global ASM command. So in our lib.rs, we're going to use a global ASM, and then the assembly text we would put here, followed by some options. In our case, we're going to put include stir and then put our assembly in a separate file. This lets us get syntax highlighting. Like, VS Code will know that this is an assembly file and then highlight it a little bit for us, which is nicer. And then we're going to put options raw as our option, so that because we are going to use curly braces a little bit in our assembly code, and you'll see why later on. But assembly strings are normally treated like Rust template strings, where like if there's like words like that in curly braces, and it tries to substitute in there, and if you want to really have the curly braces, you have to do all of them twice, and that looks weird. So if we just say options raw, it will not try to do the string substitution stuff, and then we'll just write a totally normal file. So inside of our assembly runtime, we have to maintain the assembler's state from when our file starts to when it ends. And because we are using the thumb v4t target, that's going to be an ARM v4t with thumb mode enabled by default. And that means the CPU starts in ARM mode, but most of our code is going to be in thumb mode. It's going to be in thumb mode by default for every single function. And we'll see how we can change between the two modes if we need to later. But in our assembly that's going to go at the very start, we need ARM mode because that's what the CPU is in when it boots up. So we use the .arm directive, and then at the end of our file, we use the .thumb directive to put the assembler back the way we found it, you know? Next, because the linker script is looking for this special .text.gba ROM header section, and it's going to put it before any other code, then our assembly runtime puts that section name. So this .section switches us into the section that we name here. And then at the end, we put .previous, and that makes output go to whatever section was previously output was going to. Then that's like, we don't even know, but we're going to say, oh, alternately, temporarily put stuff in this output, and then go back to whatever you were doing. Again, this is just part of making sure that the assembler always ends its state in the same way that we found it. You know, campsite rule, that sort of thing. So in this text GBA ROM header section that we made, we're going to put a few things. One is a global symbol called double_start, __ start. The name for that comes from our link script here where we have the entry point. That is not magical. Like if the entry point were a different name, then we would use a different name in our assembly runtime. They just have to match. But this is sort of the conventional entry point name, so we'll just use it. And then we have, like was said in GBA Tech, we have our branch instruction and then a bunch of stuff. Now, if we look here at the bottom, it says that the total amount of space used by this whole format is going to be, well, at 0E0 hex, the little h is for hex, there's 4 bytes. So we're going to, in our assembly, put hex E0 blank space after our branch instruction, and then this will ensure that the entire header section is blank. Loco, why is it blank? What about all this special stuff? What's with the whole format? What's going on? It's fine because MGBA doesn't actually check the header information. So again, for basic development purposes, this is sufficient. If we wanted to, we could get a program called GBA Fix. It's available through Cargo. There's also a C version that you can get. Yeah, there's a GBA Tools repository you can find, and they have a C version of it. But it's only a few hundred lines. I wrote a version in Rust that it's because it's in Rust, it's available through Cargo. So that's what I suggest that you just give a try. And then you just type, GBA fix, arguments, and then ROM name, and then it will patch the ROM to put in the select information, or just fill in like a blank header if you need it to. So for now, we put some blank space. Now our branch instruction, this is the very first thing that our program will do. And it just branches forward to a label. In this case, the label is called ASM_init. And then we put that label here. So it's going to branch past all the blank space. It's going to come here. Every time, the way you read assembly is you just read line by line. And the labels, they end with a colon right here, like that. The labels are not instructions. So ASM init colon, that makes a label, but because it's a label, then it's not program code, so to speak. After the ASM init, there's actually nothing specifically here. We're going to put some other steps in here before the call to Rust main later on, when we talk about stuff later. But for this first video, it's fine that we don't do any other setup. Eventually, after some assembly setup, such as that this data section setup that I talked about and the blank section setup, yeah, we'll do that later. But eventually, we're going to call our Rust main function. For this, we do LDR, which is load register. We're going to load register 0. In ARM mode, you can use register 0 through about 12. Technically, it's 0 through 15. But 13, 14, and 15 have like special uses. You can't use them as your normal registers. So we get 0 through 12. It doesn't matter which one we use in this particular case. So we're just going to put it in 0 because we're not using them for anything else. And then equals main will get the address of the main symbol. When the linker puts it all together, it will, whatever address main happens to end up being placed at, it will put the correct address in this part of our code. And then that address will go into R0. Then we use BXR0, which is a branch exchange, because the ARM code, when we go between ARM code and thumb code, such as any Rust code, then we have to use branch exchange instead of just branch. And this tells the CPU to swap between the two operation modes. And so I mean, you just have to do it. If we'd use branch R0 or whatever, first of all, branch takes a label, not a register. But if we like tried to do like, if we tried to type like branch main like that, that would end up failing because it would jump to the main code, but it would be an ARM state instead of thumb state, and then it would just go crazy. So anyway, we'll talk more about thumb and ARM later. Finally, after all of our code, I just put this label end of init code because when we use obj dump on our thing, like this LDR R0 equals main, the linker is actually going to insert some additional constants into the code after where the parts that we wrote are, and then it'll do a relative load from this position in the thing. All of that happens automatically, but the point is a whole bunch of constants ends up in our code. If we put an extra label, then the constants will go after that label, and it'll look better. You'll see what I'm talking about later. But right now, calling our Rust main function, it's that simple. Now, the actual... Hold on, let me just confirm. We've talked about the panic handler. We've talked about the global assembly, which we have in a separate file via include stir. And we've said that we're using no standard. Yeah, okay, I believe we're good. Now, in our example, the example has to be no standard, the same as our library is. That's just how it goes. We're also going to use no main. Now you're about to say, look, so there's a main function right there. What are you talking about? But no main makes it so that normally when you have a main function, Rust provides an entry point which eventually calls your main function. There's actually an intermediate step that you don't see. It's invisibly provided for you. In this case, we need to turn that off. We need to say, no, Rust, don't, where our main function isn't going to match the normal main function signature, and don't try to provide the entry point. We're going to handle it ourselves. So we say no main. Next, we say extern crate GBA dev streams. That's the name of our library for the streams purposes. Normally, you wouldn't have to use extern crate. However, because in an example so as small as this, like we don't refer to the GBA dev streams crate at all, it wouldn't normally link in the panic handler or the global assembly, but we need them. We put them there because they're essential. So if we use extern crate, it will force cargo to link in this crate for us. In bigger examples, we won't use extern crate like this because we will be using some of the abstractions provided by our library, and then cargo will end up, doing the right thing and linking it without us saying so. And you can see, well, let's see. So say we have, oh my gosh, where did it go? Yes, so we can run the example, we get a black screen. If we comment out our extern crate, it's going to say panic handler function required but not found. That's because it's no longer linking in this, which means we no longer get access to our handy global panic handler. Okay, now for our main function. The name main is a convention. It's just whatever, like we could change what function we're jumping to here in our assembly runtime, and then the example has to have the exact same name, and we have to use no mangle on our function, which normally all symbols in Rust have some name mangling applied so that symbol scoping works, so that way, a function in one module doesn't have that has the same name as some other function in a different module. They don't actually conflict because the name mangling like prefixes the module name onto the function name, However, We don't want that because the assembly script here, the assembly runtime, it doesn't know how about any of that name mangling stuff. We wouldn't know how to write down the name of main. So instead, we're just going to write an unmangled symbol name here, and then on our example function, we say no mangle, and then that disables all of the scoping and stuff. However, only one symbol name main could be made in the entire executable. So you don't want to go crazy with this no mangle stuff. It can be problematic, but for this one case, we do need it, and we're using it only as prescribed, only as necessary. Our function main takes no input arguments. Actually, so, gosh, this should be an extern C fn main, because the outside world is going to call it, and we want Rust to be aware of that, so that we aren't allowing it to unwind through out of here or something. You know, we want Rust to be aware of what's going on. It's going to use the CABI. We're going to accept no arguments, and we're going to return never. This function doesn't return. In fact, if we tried to return like this, by not doing the loop, it would say, oh, you're going to return a unit, but you said that it's not supposed to return. So that's fine. Technically, if we had this loop and, we said, returns I32, because it doesn't return, it like qualifies, like it'll build, but then as soon as, like, if we accidentally left the loop or anything, that could be a problem. So we want this return type never on our function. And then we do our magical unsafe command, and then we go into a loop. The loop is just, we don't know what to do. We would normally put our game loop here, gather input, update some world state, draw what we did, and then wait for more input, that sort of thing. What we're doing with this unsafe code, and we're almost at the end, folks, we're almost at the end. What we're doing with this unsafe code is that we're going to learn about a thing called memory mapped IO. MMIO, which is memory mapped IO, where we're interacting with IO devices via the CPU's memory map. The CPU only knows how to read and write to addresses. That's all it really does. But, does some math in between. But the way that it communicates with other devices is it can read from an address, and that like pulls in a signal from that address, or it can write to an address, and the write is actually like sending a signal off to something. So in this case, the address span starting with 0x04, all of this 0x04 00, that region, because remember we had these other regions in our linker script, the 2 region, the 3 region, and the 8 region. The 4 region contains most of our MMIO controls. There's some additional regions we'll learn about that contain video memory and palette memory and stuff, which we will interact with through MMIO. But that's just like, it's basically like normal memory. You just put some bytes there. Every address has special controls. In this case, this is a thing called the display control. In fact, let's say const. What's GBA Tech call it? GBA Tech calls it discpunct. And this is a mute u16 equals this number here, 0x0 as 0.u16. And then we can say discpunct.write volatile that. And we've labeled a thing. Now we're one step closer to understanding it. Now normally, if you do a write or a read, which the compiler deems is not strictly necessary, it will elide that operation. It will skip over it in the final optimized code, because it says, you write the number 3 to a particular address, and then you write the number 4 to a particular address. Well, you didn't read the number 3 while it was there, so we can skip past that. We can just do the final write. In this case, with memory mapped.io, that's not appropriate. That's not what we want. So we're using a write volatile, which says, compiler, I know what I'm doing. You must perform this operation. And then in the output, the compiler will be forced to perform the volatile memory access. It will not eliminate volatile memory accesses. This does mean that, like, if you use volatile when you don't need it, the program runs potentially slower than it could because it's not as optimized as it could be. So again, we're like with no mangle. We are using volatile only as much as we need to accomplish specific goals. We're not going to go too crazy with it. And exactly what this special U16 value, this 3 or 1 shifted 10 is, that has to do with, let's see, display control. Yes, that has to do with these bits here. So within this 16-bit address, there are different modes. So the lowest bits 0 through 2, determine the background mode. And then bit 10 is, should we display background 2 off or on? And we're going to talk about how to work with this in a better way in the next, well, maybe not in the next video, but soon enough. We'll talk about a better way to abstract that. Certainly not the only way, but like we're gonna apply a little bit of types to this, make it easier to remember. You won't have to remember, bit 1 does whatever and look it up every time. We're going to make some methods and functions and so forth. But the CPU doesn't care how abstractly you access it. So we can just write it as a very confusing looking 16-bit number, and that's fine. And then we perform the write volatile operation. This is, of course, unsafe because in the general case, not every raw pointer access is going to be valid, and the compiler doesn't know that this pointer is valid, and so we're saying, trust us, we know what we're doing. We will also, in the future, talk about how we can provide a better interface than all that unsafe stuff to access things, but that's fine. So we have this one operation, and it makes the screen turn black instead of starting off its white position, and then we loop because we don't have anything else to do. How do we, read the buttons? That's MMIO. How do we draw a picture? That's MMIO. We'll be using a lot of MMIO, so we're going to spend probably an entire episode about how to safely encapsulate different MMIO concepts that we're going to be doing. We're going to be learning about the different components of the Game Boy Advance. If I look over here, that's an ASCII art. The memory map. So there's some BIOS functions we'll learn about. The RAMs, there's all sorts of I/O registers. If we go down here, look at all these different I/O registers. So we'll be talking about that. VRAM, object attribute memory, is how you do sprites that move around the screen. Palettes, and even how to access the save RAM, I'm sure we'll touch on eventually. I'm going to put this code, I'm going to commit it, put it in the GitHub. I'm going to put the link in the description, and I don't know that there's any schedule for these, but as I have time to get ready, we'll just work through it at whatever pace. So until I see you next time, have fun.